Hello there. So I'm going to talk about a really important topic that I care, and I think that we all should care. So I'm going to talk about my process of implementing a really fast URL parser in Node.js and how it should and it will impact Node.js in the future. So before that, a little bit about me. I'm Yagiz. I'm a software architect. I'm currently a master's student in Fordham. I'm creator of multiple different packages. URL state machine is one of them, is the result of this work that I did. Other than that, fast query string. I'm a contributor to Node.js, Fastify, and many, many more libraries. So before diving into URL parsers, let's talk about the core bottleneck in Node.js's current architecture. So as you know, Node.js is a runtime on top of V8 engine. There are different runtimes, just like Dino uses V8 with Rust, Bun uses WebKit, and so on and so forth. So the thing is, whenever you call a function, JavaScript userland runs the C++ code using a bridge. So whatever you send between those bridges is serialized and deserialized. And most of the time, most of the performance talks, we have these built in, but we don't ever talk about it, but because it's a requirement. So the thing is, because C++ is much more performant than JavaScript, and because of these bottlenecks, we tend to write our computationally heavy functions in C++ side, Rust side, and we are using it through any Node API, or we are calling Webassembly in order to perform those computationally heavy functions in there instead of the JavaScript runtime. So this is a result of the problem within the performance, in terms of performance size on the JavaScript side, that C++ has more advantages of it. So let's talk about some URL parsers. So why am I actually talking about URL parsers? So URL parser is the most important functionality for a web server. It is the fundamental function that runs on every benchmark, every application that requires a network layer. So it creates the basis of these benchmarks. On top of that, every single request, locally or through internet, actually uses URL parser. So this is one of the diagrams of a request coming to a server. The left-hand side is this guy. Whenever he sends credentials through the user agent to the client, it goes to the client sends it to the authorization server, it responds back with the authorization code, user agent then redirects the authorization code to the client, and so on and so forth. So every arrow that goes from left to the right side uses URL parser. But because we all accepted the fact that this is a requirement that we do, we stopped looking for changes. So it is a really significant component, but it's too complex and leads to bugs, and that's why we tend to fear about contributing in Node.js about changing URL parsers, string decoding, encoding, and those kinds of really important things. So this is one of the issues that I've found, that while I was implementing URL state machine, I was testing these web platform tests, which are 755 ones, I guess. And while doing that, before actually questioning whether or not Node's implementation is correct or wrong, I assumed that this library is wrong. And the library's author, nice guy, told me that actually Chrome and Safari returns the correct response, but Node doesn't. So this made me question myself. So I have this fundamental thing that Node should be the correct one. I don't know, maybe I'm using Node for the past 10 years. So this leads to me opening a pull request saying that, okay, it doesn't validate IPv4 with more than 4 parts. And this is April 29. And this leads to another issue saying that URL is not compliant to specification. So this means that we somehow did not update our VPT tests, and it led to this false assumption, and it failed it. So what is the goal of a URL parser? We all know what URL is, what parser is, but let's talk about URLs. So this is one of the structures of a URL. As you know, there are protocols, usernames, passwords, hosts, path name, and search and hash. So URL parser's goal is to get this really long or really short string, and in order to parse which part belongs to which part. If you look at from there, I'm pretty sure that all of you can implement a function to handle these kinds of, like, if you see a host name, then you know that there's an @ sign. So if you slice on it, then you can get the host name. And if there's a port, you can get it. But it's actually much more complex than what you see right now. So what is the state machine behind it? This is a state machine. I'm not going to dive into details. This is the actual diagram of the state machine behind it. Really cool animation. So if you go from the start, there's a scheme start state. There's a scheme state, no scheme state. So it's actually much more complex than what I anticipated when I first started implementing this. So this is actually from the specification. Let's dive into the first two states so you will have an understanding about what it is and how it's important to read specifications. So scheme start state, so the thing is, for every character in the input of the URL specification states that you need to do this and this and this and this. So it's pretty straightforward. So if the character is a SG alpha, append C, lowercase to buffer, and set the state to schema state. Otherwise, so every edge case is handled. So this was the first one. This was the second one, no scheme state. If the base is null and the base is an opaque path, by the way, those underlined lines are actual links. If you click on it, then it will lead to much more in-depth description about what an opaque path is, what is a validation error, what makes a fragment fragment, what is the delimiter of a fragment, and those kinds of really important things. So, but why? Why did I even start doing this? Because as a graduation project of my master's program, I was looking for something to contribute in order to, like, for spending 3 months of my life, I wanted to make something different and have an actual impact in the real world. That was the goal. That was the goal of this presentation. So this was one of the issues that led me to search for it. In 2019, I think the issue is still open. There's a performance problem with the WhatWG URL API. And this contributor said that, yeah, okay, we need to solve this. And they actually did some benchmarks there, which means that, yeah, it's pretty clear. So what are the potential solutions? There was this really great issue by James that what about let's implementing the URL parser from Webassembly. So he made a really great argument saying that, like, it should be possible to realize a significant performance improvement by porting the implementation of Webassembly. So I said, okay, let's do it. It's pretty straightforward, right? I need to read the URL specification. I need to rewrite it in the language of my choice. I need to compile it, and then use the WebAssembly as a bridge, and then voila, everything is perfect, but not. So what are our options right now? So the initial assumption was that to use a WebAssembly. So yeah, we can do a WebAssembly. We can use Rust. We can use Node API, or we can just go with JavaScript. But it's not the fast API. So this is one of the issues. If you're one of the core contributors of Node, you will see that most of the issues receive a really good comment saying that let's use fast API. But no. So what are the potential solutions? We can compile C, C++, or Rust to WebAssembly, implement our own URL parser in there, or we can use Node API, or we can just use pure JavaScript. So I'm not going to talk about an API today. I'm going to talk about WebAssembly and pure JavaScript implementation. So the expectations. Initially, I started implementing the URL parser in Rust, and my expectations were, it's proven that Rust is super performant. There are really great talks before me saying that it is. They had some examples. That's true, but not for every case. So WebAssembly and Rust is a really good duo, thanks to Firefox. Undici is a really good example. If you go into the README, there's like a really good description saying that there's like a 1,329% performance boost with WebAssembly because that's the fact. But in reality, decoding UTF-16 to UTF-8 is costly. WebAssembly communication relies on shared memory. So this means that whenever you want to pass a variable from JavaScript userland to WebAssembly to another language, you are using a shared memory. That means that you need to decode and encode in order to put your values into that shared array buffer. So shared memory requires decoding and encoding. And text encoding and decoding in Node.js relies on C++. And those are the two, our only solution to encode and decode in a really fast way in Node.js for serialization, text encoder and decoder. So why did we end up with text encoders? A quick recap. So let's talk about where we started. We are trying to improve the existing implementation, which is based on C++, which uses which calls JavaScript userland to C++ side. So there's a serialization process going on there. And most of the time, if you want to improve a performance of a certain function, we just need to eliminate that network, the latency between those two userlands. So improving by removing the C++ bridge, but text encoding and decoding in Node.js relies on C++. So let's do a benchmark. This is one of the screenshots. This is like a really early implementation of using URL search params only in Rust, and then I was comparing it to the native implementation. For setting a URL search params, it was 86% slower. For appending, it was 96% slower. For actually initializing a URL, it was 24% slower, and this didn't include the full specification implementation. This was just initially grabbing some certain things, and so yeah. So it's 86% slower. When I say 86%, that's not a random number. That's a fact, which is so sad that I need to put it in this really big font. So let's start again. I'm Yagiz. I'm going to talk about URL parsers today, and the topic of my talk is, can we write a fast URL parser using JavaScript? So why JavaScript? Because there are another solution that does not use the C++ bridge. So I'm kind of limited by the technology of my time. And that's why the URL state machine library actually got developed. So as a result of my work and as a result of following this spec, I developed a library called URL state machine, which is pretty easy, has a similar interface, just like any other libraries. You can actually pass a URL, it grabs, it divides. So this is the only requirement and the output that should be produced by a URL parser. Other than that, what you see on URL search params uses the state machine in order to manipulate your input. So if you want to say, OK, I want to change the fragment of a URL, it actually calls the URL state machine in order to update it. So let's do some benchmarks. If you pass this google.com and the path to something hello world string, then URL state machine is actually 576% slower than the other JavaScript-based implementation, but it's again 85% slower. And this is after all of the work is combined. So what are the optimizations that led to this change? But before that, I'm going to talk about I want to tell you about something else. So if you look into a benchmark, you can see that it's 576% faster, right? I can easily manipulate that input in order to produce a result that benefits my own library. This means that if I decrease, so because I know how URL state machine is implemented, if I reduce to the first implementation, the first path to something to a shorter string, or if I didn't use schemas in the http google.com, then I would have a better result. Or if I increase the length of the input to 200 characters, the difference between, in terms of performance on the native side and the Euro state machine will be much more higher. It won't be 85%, it will be 850% slower than the actual implementation. So that's one of the things that I want to mention, because benchmarks, even though they're really great, it's really easy to tamper with. So what are the optimizations that I did and what you should do in your libraries and on your applications too? So one of them was that using function versus class, I achieved a great performance boost by just changing my classes into functions. And while searching this on GitHub and Google, Rob actually sent me this tweet saying that this is fixed in V8 9.7. And classes was introduced in, let's say, 3-4 years. So this means that the new features that we tend to use in JavaScript is not as performant as it should be. And by just changing class to functions, you can have a better performance. And V8 9.7 was included in Node 17. I think Node 18 is higher than this, so Node 18 fixes it. But if you're using Node 17, then that's a really bad thing, right? So the other thing is using if versus switch. There's an issue in the Chromium repository from 2012. The performance of switch is really bad, and they did some benchmarks and they talk. But the thing is, in reality, if you there isn't any exact science behind which one is faster right now. But the thing is, if you're using less than 10 parameters, using an if statement is faster. If you're using more than 10, using a switch is faster. So in my case, because I had around 12, 15 different states, changing my code to use switch did actually improve my benchmarks. So the other one is that this was a really great recommendation from James, was to just replace strings, because I was using string in order to set the state. If you use a number instead of a string, it would be much more easier to compare, because if you're comparing two different strings, what would be the most naive approach to compare? It would be first check the length of the two strings. Then, character by character, make sure that all of them is equal. And then, at the end of those for loops, if it's OK, then it's equal. So that's an ON operation. But in numbers, that's not the scenario. So this was one of the changes that I did, just introducing a state, just putting some numbers in order to define my states, and actually changing the code. And then it improved it a lot. On the other hand, this included doing lots of micro benchmarks, which means that for really small operations, for my use case, I had to do micro benchmarks on whether I should use slice or substring, because slice creates a new string, substring returns a copy of that particular string. So slice was faster. This is one of the changes that I did, which improved the performance. And on top of that, the actual specification says that you need to have a code point and whether or not that code point is valid or not. So code points are numbers, and in order to check for if it's a valid number or not, is not a number, is the correct way to do it. But the thing is not a number, is a costly operation. But if I just check for undefined, whether or not it's an undefined or not, it's again faster. So this leads to this code base, and right now, as you can see, I'm working on some micro benchmarks. If you look from an outside scope, changing is none to checking for undefined seems like a really small thing, but if you run it a million times on a benchmark, you will see the actual difference in the true output of it. So again, this is one of those changes, which came to the most important optimization of all, memorization, which means that I should cache some certain things in order to improve my performance, so I don't need to check it every time because I have a pre-computed value for that attribute. So this is what I did. So one of those, according to the specification, you need to check if the schema that I'm currently in is a special schema or not, which means that is the URL contains HTTPS. or FTP, or like those kinds of special schemes. So if I just use it as a variable after I read through the scheme state that I first told you about, then this is like a really great performance improvement, right? Yeah, that's correct. But the thing is, if you see some pattern, right now, I'm starting to change the URL specification. URL specification and tells me to check it, and I'm in order to improve my code in the language that I'm using, I'm changing how the specification is implemented. So this is the issue. You can always get better results, but in different runtimes, in different applications, but for certain things, if you stop following specifications, it will be always open to more bugs and more complex scenarios that maintainability and readability will be decreased. So let's give some statistics about the work that was done. It was 1,976 lines of code, 800 plus benchmarks was run. It is 99.9 spec compliant. Only one test was still failing, which I don't have the patience to fix it. On top of that, there are 733 successful web platform tests were run, and only 95% of code coverage. So this means that the web platform tests that are suggested right now does not cover every case. So this is something else which I'm quite shocked that it's not 100%. But yeah, it's important to talk about. So in terms of performance, yeah, it's 576% faster, but it's 85% slower. So great power comes with great responsibility after V8 fixes this performance problem. So there's a lot we can do, but the thing is we are bounded by V8, and yeah, there's literally nothing that we can do right now at a certain level. So a small footnote, this work that I represented is actually a work done on 3 months with lots of great engineers. So I want to thank William Lord, James Snell, and Matteo for helping me and guiding me through this process. And thank you for listening.